Welcome to Who Shaves the Barber, a weekly podcast where we explore paradoxes, thought experiments, and other pointless problems. I'm William Nava. Last time, in part 1 of this 2-part episode, I introduced the liar paradox. If you haven't listened to part 1, make sure you do so before listening to this one. You can find it at williamnava.podbean.com. In part 1, I left off with the problem of identifying what drives the liar paradox, and which of the many paradoxes that seem similar to it are actually of a kind with it. This issue is important because of the principle of uniform solution, the idea that paradoxes that are of a kind should have the same solution. Now, the principle of uniform solution itself maybe has some problems, so let's consider two possible problems with the principle of uniform solution. Here's one problem. What about the Barber paradox? The Barber paradox seems to actually have the same structure as the liar and Russell's. It has the punchline is that same loopy contradiction. If he shaves himself, then he doesn't shave himself. If he doesn't shave himself, then he does shave himself. And we seem to get there through a similar kind of self-containing, self-referential process. So, does that mean that the Barber paradox has to have the same solution as the liar paradox and Russell's paradox? Well, we found the solution to the Barber paradox. It wasn't really a paradox at all, but what was going on was that we were able to just deny the premise. Right? And we said it's not really a paradox, but that's because the premise didn't seem to really be true, but we can imagine something like the Barber paradox where we can just discover that there's something about one of the premises that's just off, and it's very particular to this example, right? To this particular paradox. So what we discovered there is there's no reason to think that this Barber actually exists. It's not nearly as easy to say, for example, this totally abstract collection of things called Russell's class doesn't exist, or this sentence doesn't exist. So it doesn't seem obvious by any means that the solution to the Barber paradox should be the same as the liar and Russell's paradox. So that would maybe seem to be a problem. I think it's really more of a caveat than a problem, and the caveat is this. It's always possible that some particular paradox will have some idiosyncrasy to it that will allow us to solve it in a sort of easier and in a way that doesn't address the underlying phenomenon, let's say, right? That there's something about the way a particular paradox has been created or set up that allows for a solution that doesn't get at this deep thing. It's just an easy, so to speak, mistake. And so in those cases, we don't have to think that there's going to be a uniform solution, okay? Now, the second problem, I think, is a little bit more serious, and that is the problem of at which level we're talking about when we're saying that we have these shared structures. So here's what I mean. On a trivial level, all paradoxes share the same structure, okay? All paradoxes have apparently true premises, apparently correct reasoning, and an apparently false conclusion. By definition, right? That's what makes them paradoxes. Okay, so does the fact that all paradoxes share that structure mean that all paradoxes have to have the same type of solution? In a sense, actually, yes. All paradoxes have to have a solution that either rejects one of the premises, revises one of the rules of reasoning, or accepts the conclusion, right? And so maybe the answer to this issue with the principle of uniform solution is that the level at which the structure is shared by the paradoxes is also going to be the level at which they must share a solution, right? That there are sort of levels of specificity at which a structure is shared, and it is at that same level of specificity that you're going to have the same type of solution. I think that you have to also have essentially that caveat in order for the principle of uniform solution to work and to be insightful. But I think if you have those two caveats, the principle of uniform solution does make sense and does seem to be true. I mean, at least intuitively, it does seem like it should be the case, right? Our solution should get at this underlying phenomenon that's creating these paradoxes and not just, solve them in totally different ways. Okay, so now how do we know whether two paradoxes do share the same structure? How do we know whether something is in the liar family or isn't? As we said, the liar is similar both to the truth-teller paradox and to Russell's paradox. Which of those should we really consider the family of the liar paradoxes? So there's something called the Inclosure Schema. It was originally proposed by Bertrand Russell when he was working on Russell's paradox and also noticed that the liar paradox had the same structure. And it's been recently brought back into the fold of popular philosophy discussion by Graham Priest, who's written about it. The idea is those paradoxes that fit this scheme, essentially this structure, are of the same family. So it gets a little bit technical, but I'll do my best to make it as simple as possible. Here's how the enclosure schema works. You start with a class of objects defined by some property. So, for example, the class of classes or whatever it is, right? And then you have a function. Okay, so this is a function that acts on a subclass of that original class. Okay, so we have a class defined by some property. Okay, the class of all red things, whatever it may be. Okay, then you have a function, and this function acts on subclasses. So you might have the subclass, for example, all red things in New York is a subclass of the class of all red things. So maybe the function can act on that. Or it can act on any subclass, right? That's how the function works. And what the function does is that it acts on that subclass, and by acting on that subclass, it outputs an object. What is the object that it outputs? It has to be an object that meets two criteria. Okay, and Peirce calls these criteria transcendence and closure. Transcendence is the object that is outputted is not a member of the subclass that the function acted on. That's transcendence. The object, however, is still a member of the original bigger the original bigger class defined by the property. That's closure. Okay? So that is the enclosure schema. And the way it yields paradox is that when this subclass that the function is acting on, remember the function can act on any and all subclasses of this big class. When the function acts on the subclass that is actually the whole class, right? So the whole class itself is technically a subclass of itself. It's the subclass that is the whole class. Then, in order for it to meet transcendence and closure, it has to not be in the subclass, but it has to still be in the original class. But now the subclass is the original class, which means it has to both be and not be in that class, in the original big class. That's the contradiction. Okay, so that probably sounds really confusing, but let me go through some examples, and I think it'll start to make sense. Let's start with Russell's paradox. So Russell's paradox, we start with the class of all classes. That's the original big class. Okay, the function when you apply it to a subclass, it yields another class. Okay, it yields a class that's defined as the class of all classes in this subclass that are not members of themselves. Okay, so let's run through that. So it yields a class of classes in this subclass that are not members of themselves. So now let's see if this class that's been outputted meets transcendence and closure. Okay, so let's look at transcendence first. Is the class going to be a member of this subclass that the function's acted on? Well, let's look at it, right? Let's first ask, is this outputted class? Is it a member of itself? Well, in order to be a member of itself, it has to meet the criterion, right? The defining criterion of itself. And one of the defining criteria is that it be non-self-membered. So it couldn't be self-membered, okay? So it's gotta not be a member of itself. Now, so it's not a member of itself. But now let's also look at this. If it were also a member of the subclass that was originally acted on, and it's not self-membered, then it would meet all the criteria that defines it, and so it would be self-membered. Okay, this is just Russell's paradox. If it were a member of that subclass, then it would have to both be a member of itself and not be a member of itself. That's a contradiction. But what's going on here is that we can avoid the contradiction by just saying, no, this class is not a member of itself and not a member of the subclass that the function originally acted on. Okay, that allows it to not meet the criteria of the class that the function has outputted. Okay, and so we don't have a paradox. We've just got a function that acted on a subclass, outputted another class. It's not a member of that subclass, and it's defined by this property of saying it's the class of classes in the subclass that are not self-membered. We don't have a paradox, no problem, and transcendence is met. Also, it is a class, this output object, and so it is a member of the class of all classes, which is the big class we started with, and so we do have closure. We've got closure, we've got transcendence, we've met the requirements of the enclosure schema, and we don't have a paradox. When does a paradox arise? When the subclass that the function acts on is the original big class. Then we can no longer say, oh, no problem, the class just isn't a member of the subclass because the subclass is the original class and it's got to be a member of it just by virtue of being a class. So now we've got a class that is and isn't a member of itself. We've got Russell's paradox. Okay? So this probably, if you look, it might sound a little bit complicated, but if you look at it, it's really just a way of formalizing what's going on in Russell's paradox. And the reason to do that, as we'll see, is that we're going to see that you can do the same thing with the liar paradox. Before I get to that, I want to make sure that the enclosure schema is clear, because I know it's kind of a complicated thing. It's usually put forward more in a kind of with symbolic logic, but I think it can be understood in just simple kind of language. So first I want to clarify something about this whole idea of the subclass, right? So I've said the function acts on a subclass of the original class. Let me just kind of give an example of what that would look like in a case other than the case where the subclass is the original class that creates the paradox. So let's have the subclass, the class of all classes that have only 5 items in them. Okay, so when the function acts on that subclass, it's going to output some other class which will meet the criterion defined by the function, which is being a class of classes in the subclass that are not self-membered. Now, is that class itself, the output class, in the subclass? Well, you have to ask, one of the defining criterion for being in the subclass was having only 5 items. Does this output class have only 5 items? That is to say, are there only 5 classes that themselves have 5 classes and aren't self-membered? The answer is no. You can just abstractly create an infinite number of those. And so you see sort of through that kind of reasoning why that output class wouldn't be in that subclass. So that's just kind of as an aside to give an example of this, another example of this subclass. Now, I want to run through the enclosure schema with the Barber so that you're a bit more familiar with it. And then we'll go through it with the liar. Okay? So with the Barber, If you remember, the Barber paradox is we have a town and there's a barber who shaves everyone in the town he shaves everyone in the town who do not shave themselves. So let's start with the original, the top class, the class defined by some property is the class of all people in the town. Okay? Now then we've got that function that acts on a subclass, right? And that function, what it outputs is it outputs someone who shaves all members of the subclass that do not shave themselves. Okay? And so now we can ask, is this output person going to be a member of that subclass, right? Is this output person going to meet transcendence? If he were a member of the subclass, okay, then that criterion of being of the class, the output person is somebody who shaves everyone in the subclass who does not shave himself. So if he were in the subclass, then right away he's in the domain of people that gets applied to. Okay, so then he would have to shave himself only if he doesn't shave himself, would be at the Barber paradox, right? But if he's not in the subclass, then he's not in the domain of people that gets applied to, and so we avoid the Barber paradox. There's no, right? Then we don't have a problem, but we do have transcendence, not in the subclass, and we do have closure. Okay, so we've got something that fits the enclosure schema, and we don't have a problem until the subclass is the original class, because when the subclass is the whole class of people in the town, then by definition he's a member of the town, so he's got to be a member of the subclass, so he's got to be in the domain. Then he would have to shave himself only if he doesn't shave himself, and we're at the Barber paradox situation. Okay, so I hope that makes sense of how the enclosure schema works. So how does it apply to the liar? Okay, with the liar, the starting class that we work with is the class of all truths. Okay, the class of all true sentences, let's say. The function, when applied to a subclass, outputs a sentence that says, this sentence is not a member of this subclass. So now let's look at it. Is the sentence itself a member of the subclass? Again, let's start by looking at whether it's true or false. If the sentence is true, then what it's saying is that it's not a member of the subclass. So it wouldn't be a member of the subclass, and we wouldn't have a problem. It just wouldn't be a member of that subclass of true sentences. And so we'd have transcendence, okay? And because it's true, we'd have closure. No problem there, right? The sentence wouldn't be able to be false, because if it was false, then what it's saying is that it's not in the subclass, so then it would be in the subclass. But this is a subclass of true sentences, so then it would be true, okay? So in order to avoid any kind of contradiction, we have to accept that the sentence is true, but not a member of the subclass. In other words, we'd have transcendence and we'd have closure, okay? Now, the paradox arises when the subclass is the whole class of true sentences, because then by virtue of not being in the subclass, it would have to not be a true sentence. And so we've got that if it's true, it's false. If it's false, it's true. We've got the paradox. Okay? So this is how the liar paradox also meets the enclosure schema. And so now we've got the argument. Look, the liar paradox and Russell's paradox, they both meet the enclosure. They both satisfy the enclosure schema. They can both be broken down into this shared structure. You know, and actually the fact that the shared structure seems so kind of complex in a way would seem to say that's actually a good argument that, you know, this is a pretty specific structure and they both meet it, and so they both must be of the same kind. And that's intuitively what we would have thought. And, you know, let's say the truth teller paradox, for example, doesn't meet this schema, and so truth teller paradox is of a different family. Okay, so now let me summarize for a moment about the enclosure schema. Let's sort of step back from the formality of how things fit into the enclosure schema, and let's just look at what it's really doing. It seems to work fundamentally with a function that yields something that is and isn't a member of some category when it's applied to the class of the category itself, right? And if we just look at that intuitively, that actually does seem to be what's going on with both Russell's paradox and the liar paradox. It's not as immediately obvious with the liar paradox, but once we think of the liar paradox as dealing with the category of being true, then it actually does seem to make sense, right? So intuitively, the enclosure schema does seem to be getting at the fundamental structure of what's going on with these paradoxes. Now, there is a problem with the enclosure schema. So I mentioned earlier that the enclosure schema has recently been popularized by Graham Peirce as a way of analyzing what's going on with these paradoxes. So Graham Peirce has shown that the enclosure schema also applies to the Sorites paradox. So very quickly, I'm going to cover the Sorites paradox. I don't want to do it in a lot of detail because I'll do that in a different episode. The Sorites paradox is its own monster. It's its own whole world. But roughly, this is the Sorites paradox. Start with an object that is clearly red. Just paradigm case of red. And let's take the principle called the tolerance principle, which is that if you have something that's red and you make it imperceptibly less red, just a couple of whatever, just a tiny bit of wavelength less red, but small enough of a change that you can't actually see the difference, then the resulting object is also red. Okay? So no matter what object you start with, if it's red, then when you make it imperceptibly less red, it'll still be red. So now start with an object that's clearly red and apply the tolerance principle, get another object, still red, apply the tolerance principle, get another object, still red. Now do that 1,000,000 times and you'll have a blue object, let's say. And according to the, to reasoning and to the fact that the tolerance principle works, the resulting object will still be red. Okay? That's the Sorites paradox. So again, I'll do a different episode about it. At first, I think often it doesn't seem like it's a serious paradox, but there's some issues there. But what's relevant here is that Graham Peirce has shown that you can use the enclosure schema to describe the Sorites paradox. Now, for Peirce, what he's doing with that is actually he's used that to argue that the Sorites paradox is of a kind with the liar paradox and with Russell's paradox, and that therefore they should have the same solution. I think that's fairly absurd, because intuitively it just seems fairly obvious, actually, that what's going on with the Sorites paradox is just totally a different phenomenon. That's what's going on with the liar and with Russell's paradox, right? With the liar and Russell, there's this self-reference negation thing going on, and with the Sorites paradox, what's going on is that the properties like red are vague. Okay? So it just seems like they have nothing to do with each other. And so actually it seems to be a failure of the enclosure schema that it can apply to both, if the purpose of the enclosure schema is to categorize what counts as being of a certain family of paradoxes. Now, I think we can salvage the enclosure schema, because in the enclosure schema, the function does most of the work. Okay, so if we look at everything we did when we applied the enclosure schema to these paradoxes, most of what was going on was just setting things up in the language of classes. Okay, it's the function that really did the work of creating the paradox. It's the way that the function was defined that really did the work. And in the case of the Russells and the liar and the Barber, the function always involved some kind of self-reference, right? It always involved this idea of not being a member, right? It always had that self-reference negation thing going on. And when you put the enclosure schema to the Sorites paradox, that's not the case, or at least it's not obviously the case. And so I think we can modify the situation and say that things are of a family, like things are, let's say, of the family of liar paradoxes, if you can apply the enclosure schema to them, and the function in the enclosure schema involves, let's say, self-reference and negation. There's probably a more precise way to put that, but I think that gets at it. Okay? That allows us to use the enclosure schema to still explain what makes the liar and Russell's of a kind, and not have the kind of absurd conclusion, I think, of having the sororities paradox be of a kind as well. Now, there's something I want to mention, and that is that there is a slight difference with how the liar paradox was mapped onto the enclosure schema and how Russell's paradox was mapped onto the enclosure schema. The liar paradox seemed to be more directly self-referential. Here's what I mean. The object that was outputted by the function when we did the liar paradox, it outputted a sentence that was already self-referential. It outputted a sentence that already said, this sentence is blah, 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 right? Not a member of the subclass in that case. With Russell's paradox, it outputted a class that had as members classes that were defined self-referentially. They were defined as not being members of themselves. Okay, so it outputted an object that contained within it objects that were defined through self-reference, as opposed to the liar, where the output object was already self-referential. Notice that the Barber worked the same way as Russell, right? The Barber, the function outputted a person who shaved people that did not shave themselves. So it was the people that the output person shaved that had the self-referential property. Okay, so there is that slight difference. It seems like with the Barber and with Russell's paradox, there was like an extra step, right? And I think that's because Russell's paradox and the Barber paradox both are set up as paradoxes about belonging to some category, whereas the liar paradox can be set up that way, but the way it's normally set up, it's already self-referential. It's directly self-referential. It's not about necessarily belonging to a category of, let's say, things that are self-referentially defined, right? So in Russell's paradox, the issue is we've got a class, and then the members of the class have the self-referential property, and then when that gets applied to the class itself, we've got a paradox, right? In the case of the liar, we've got a sentence that is already directly self-referential. It's not, at first glance, dealing with categories. I mentioned this because earlier I said that the extent to which the principle of uniform solution should apply has to do with the level at which the structure is shared, right? So in the case of Russell's paradox and the liar paradox, I think it's pretty clear that they do have very similar structures at a fairly specific level, right? At a level as specific as you can apply the enclosure schema, and you can apply the enclosure schema in such a way where the function involves self-reference and negation, right? But it's not a shared structure all the way. Once you get to a certain level of specificity, there's a way in which Russell's paradox and the Barber, and then there's other paradoxes as well that apply in one way, and then there's a slight difference with the way that the liar does. And so that's to maybe note that, maybe there are slight differences in the way that the solutions to the two paradoxes should work, right? Slight differences, maybe. Differences at that level of specificity of the structure. Now, how that would actually play out would have to involve looking at what the proposed solutions are, so I'll leave that at that. So let me kind of now conclude this whole discussion about the types of paradox, the what counts as being in the family of being in the liar paradox. So I think it's fairly clear to say that the truth teller paradox, for example, is actually of a different kind. At first glance, it seems to be similar, but it's actually a fairly different paradox. And we'll see that's kind of its own family. There's other paradoxes, such as the no-no paradox, which is a really cool one. I'll do an episode on it later. That is of a kind with the truth teller, whereas the liar and Russell's paradox, though there is that slight difference, clearly are of a kind, and we can use the enclosure schema to identify that. Now there's a whole family of paradoxes that share a structure with the liar and with Russell, and some of them kind of closer to Russell, some of them closer to the liar, based on that one difference that I noted. So, for example, I'll give a couple of examples of these, and some of these I'll do episodes on later, and some of them probably not. So one that I probably won't do a full episode on is the Infallible Seducer. The Infallible Seducer is kind of a joke, but it has the same structure if you look at it. And it goes, there's a there's a guy, let's say, that wants to seduce a woman, and so he asks her 2 questions in succession. The first question is, will you answer the next question the same way that you answered this one? And no matter what she says, he then follows up with, will you sleep with me? Okay? So if she answers the first question with yes, she's saying that she'll answer the next question the same way as this one, so she has to answer the next question with a yes. And if she says no to the first one, then she's not going to answer the next question the same way as she answered the first one, and assuming she can only answer yes or no, then the second one has to be yes. So either way, the answer to the second question has to be yes. You can kind of see how it's doing the same sort of thing as the liar, and it's got this, whatever, humorous aspect to it. Then there are, I mentioned already, the properties version of Russell's paradox. Another one that's more similar to the liar as opposed to Russell is the knower. Okay, so this is not known. Works a lot like the liar paradox, but brings in this whole issue of knowledge as opposed to truth. Then you've got the set theoretical paradoxes. Russell's paradox is one of those. It's probably the simplest. But then you've got others, and they deal with set theoretical concepts, like being well-founded or being an ordinal. So I think I'll probably do an episode later on about the set theoretical ones in particular, where I'll go more heavily into Russell's, but then I'll mention some of these as well. And there's a bunch others. There's Berry's paradox, which is a really cool one about least definable number. There's the Nelson-Grelling paradox, also known as the heterological one, which I'll also talk about in a different episode. And there are a few others that are meant to kind of challenge the issue of whether the liar has to be self-referential. So I'll actually come back to those at the very end. Before wrapping up the episode, I realized that I haven't actually gone into any solution with any level of detail, right? So only discuss what the types are. And so I want to leave you with one proposed solution, one that I think is fairly obviously false. Doesn't work, but that way we can say we at least tackled a solution in this episode. And that is a solution proposed by C.S. Peirce. And it's the idea that sentences automatically assert their own truth. Okay? So the idea here is any sentence, no matter what it's saying, it's also saying that it itself is true. Now, this is an interesting idea, and it's kind of compelling, right? If I say I did your laundry, it's implied that I'm also saying, or that at least I would also agree with the idea that it's true that I did your laundry. So the idea here is this sentence is false, is actually saying it's true that this sentence is false. That amounts to the sentence saying this sentence is true and false, which means it's outright stating a contradiction. And the fact that, so if it's outright stating a contradiction, then we don't have a problem. Then we can just call it false, right? If I say, I have a cat and I don't have a cat, then it's not like I said something mysterious, right? I'm just lying. I either have a cat or I don't, right? So here, again, we can just, if the sentence is really saying this sentence is true and false, then we can just avoid all the problems and say this sentence is just false. And actually, let me sort of reason through it a little bit more carefully so you can see that, right? If it's true, then it's true and false, which means that it's false, which means we're back at the paradox. But if it's false, then it's not the case that it's true and false. And so it's not the case that it's true and false. It's just false. No problem, no paradox. Nope, woohoo. Now, why doesn't this work? Well, so the thing that the sentence is referring to has actually shifted from one version to the other, right? So in this sentence is false, the subject of this sentence is the whole sentence, this sentence is false, okay? When you add, it's true that this sentence is false, now this sentence is talking about the whole sentence, the one that's saying it's true that this sentence is false, right? And so we're now talking about a different sentence. And so it's not just the same sentence and then asserting the truth of that, but rather a different sentence. It has sneakily shifted subjects to be about a different sentence. Okay? So if we did believe and want to agree with this automatic truth assertion thing, then the correct way to play that out would be to say, it's true that this sentence is false, is false. That would be simply asserting truth of the original sentence, this sentence is false. And that actually doesn't add anything or change anything to the paradox. You still get the paradox in the exact same way. Okay, so this is an example of a solution that Peirce considered for a while. He later saw that it was mistaken. I suppose in terms of the categories of types of solutions, it would count as an attempt at modifying a rule of reasoning by introducing this whole idea of automatic truth assertion. But it doesn't work simply because it's a mistake to say that if you have automatic truth assertion, then the sentence actually asserts both truth and falsity of itself. It would instead simply assert that it is true that the original sentence is just false, which doesn't do anything, doesn't actually change anything. So I think that we can set that one aside as just a mistake, but it was a solution that was considered by a fairly prominent philosopher. He also has other solutions, including that the sentence is meaningless, which is also a solution that he later came to consider wrong. And we'll look at that in a different episode. Before we look at that, I will come back. So I'm going to do another episode fairly soon about the liar paradox, in which I'm going to consider possible objections to the idea that it is necessarily self-referential. And I'm going to talk about two variations. They're called Diablo's paradox and Quine's paradox. And those are kind of meant to be counterexamples. They're meant to be paradoxes that clearly seem to belong to the same family, but avoid the same kind of self-reference that the liar does. And so would seem to be compelling cases for the idea that self-reference is actually not the fundamental to what's going on with the liar paradox. So we'll look at that, and then after that, I'll start doing some episodes about the proposed solutions. And that concludes today's episode of Who Shaves the Barber? Next week, I'll be speaking with epistemologist Jim Slagle, professor of philosophy at the University of Portland. We'll discuss his theory of the epistemological skyhook, an argument that claims to show that naturalism and determinism are epistemically self-defeating. Again, I'm William Nava. You can check out other episodes, as well as my other philosophical and artistic work at williamnava.com. And if you'd like to subscribe to this podcast, go to williamnava.podbean.com. Thank you so much for listening.